Going to do some friction problems here. 23 through 29 odds. So let's see what we got here. We got 3 blocks in this figure. They're released from rest and they accelerate with a magnitude of half a meter per second squared. Block 1 has a mass of 1. So we got, let me make a little sketch of it here. I think we did a problem just like this in the last chapter, but we didn't know how to model friction then, so I think that was a frictionless one. So this is 1m, 2m, and 2m. And want to find the coefficient of kinetic friction. So they're all moving because this is bigger than this. If it's released from rest, we know that they're going to accelerate in this direction. So that's the winning direction for all of them. So let's make our 3 force diagrams for these. Forces on this one, got mg worth of gravity, and then tension here. Now there's this rope, string, whatever it is here, and that's attached to, there's a mass here, and then there's another string. So the tension here and the tension here, those tensions are not equal, and we know that they can't in fact be equal, because if they were equal, then this right here would be stationary, right? So I'm going to call this T1. And on this block here, this is the trickiest one, I think. We've got 2 mg worth of gravity, the normal force. Those would be equal to each other. And then I've got 2 tension forces, T2 winning, T1 losing. So these are equal. And then there's also kinetic friction. So since it's moving this way, friction opposes the direction of motion. So I'm going to put that here and just tuck it in there. There's my friction force. And then this block here, I've got 2 mg winning versus the tension in the second one, and those two would be equal. Okay, so sum of all forces equal to mass times acceleration. So here I've got mg winning minus T1 losing is equal to big M. The mass of this is one of those big M's times A. The A is 0.5. I'll put that in at the next step. And sum of all forces here equal to mass times acceleration. Mass of this one is 2m. So here those balance out. No motion in the up-down direction for this block. T2 is winning, and T1 and friction are losing. And that's equal to the mass of that block times acceleration. And then here, another block with mass 2m, and there's that. And I'm going to add them all together now, and hope that all the well, I'm not going to hope. I know all the t's are going to cancel out. Oh, you know what? I messed this up, didn't I? This block's going up, so T1 is winning. It did not look like that in my picture. And, you know, actually, what I was just going to say is I know they're going to cancel out, and that's how I caught my mistake. As I looked at those 2 T1s, I was like, wait a second, those are both minus T1. Those aren't going to cancel, but we caught the mistake by knowing that they need to cancel. The 2 tensions can't both be in the winning or losing direction. One's got to be winning and one's got to be losing. It's impossible for it to be otherwise. So when I add all of the things together on the left-hand sides of these equations, all the tensions are going to cancel out. I've got 2mg minus mg. So by 2mg minus mg. That cancels, that cancels, that cancels, and then minus friction. And then here I've got MA, 2MA, 2MA, that's 5MA. And then I'm going to make a couple substitutions here. I know that kinetic friction is equal to mu times the normal force. So that's mg is equal to, minus that frictional force on this block here is equal to the coefficient of friction, which is what we're trying to solve for here, times the normal force, which would be equal to 2mg. And then this A right here, that is 0.5. So that'd be 2.5 m. Right? So I think we're good. The m's are going to cancel out here. And if I move that to the other side, what do we have? I've got g minus 2.5 is equal to mu, which we're looking for, and then I could divide by 2g. And I don't think we're looking for an answer like that. I think we're looking just for a decimal answer. Let's see if I got the right thing. 9.8 minus 2.5 divided by 19.6. That's what 2g is. I got about 0.372, looks like. They had 3 sig figs on that, so that's what I'm going with there. And that was number 23. They just did 0.37. Huh. There you go. So we got it. That seems like a lot of physics to do there, but it's pretty methodical. Make the force diagram for each one, set up your equations. Got to be careful as you go through. Attention to detail is important. Number 25. Got block B tied to a knot, and then there's another string here, this angle theta, and then this going down. So the weight of block B is 711 newtons, and so will be the normal force then. And the coefficient of static friction between the block and the table is 0.25. And this angle is 30 degrees. Assume that the chord is horizontal right here. And find the maximum weight of block A for which the system will be stationary. Okay, so we're balancing things out with that amount of friction. So that would be mu times the normal force. That's how much we would have there. And if we're balanced, then that means that this tension right here, I'm going to call that T1, would be equal to this. Got to use a different number of slashes there. And then what about the forces acting on block A? So everything is stationary, which means block A with its unknown mass times G would be equal to, this is not a normal force supporting it, it's a tension. So I could call that T1, maybe this could be T2. And then I'm going to also make a force diagram for the knot, because that's definitely forces acting on that. And what are those forces? Well, there's T1 this way. That's the same rope as that. There's T2 that way, which is equal to mg, right, because this block's not moving. And then there's T3 this way, and this would have to be equal to that T1, right? Because this is, everything's balanced. And then this right here would have to be equal to the T2, that mg, and this is 30 degrees. All right, so let's see what's equal to what, and if we can chain our way back through to get an actual value for this. So mg is equal to T2 right here, and that is equal to this. So mg is equal to T3. I'm going to write this down. T3 sine 30, right? This has to be equal to that, which is the same as this, which is the same as this. And that gives me this equation right here, right? mg is equal to T3 sine 30. Okay, and then how about going this way? The force of friction, which is 0.25 times the normal force, which is 711, that is equal to T1, which is equal to T3 times the cosine of 30. So I think we got an equation here. If I do, let's see, so that's 1/2, so T3 is equal to 2 mg, and then T3 here is also equal to, if I divide both sides by cosine 30, that is 205 newtons. So there you go. So 205, that's T3, so that must also be equal to 2 mg. So if I divide the 205 by 2g, then I get a mass for block A. And they gave, was I asked for the weight of it instead? Yeah, the weight. So the weight of it is the same as the gravitational force of it. So the weight, or in other words, gravitational force of that would be 10.5 g, so I'll just multiply that by 9.8 and get about 103 newtons. Our book rounded that to 100, 2 sig figs, 1.0 times 10 to the 2. All right, these problems are a little harder, but we can do it. 27. Ooh, I like this one. Let's see. Got a 40-degree ramp. Pulley, other block. The weights of the blocks are 102 newtons and 32 newtons. And the coefficients of friction are 0.56 and 0.25. And they want to know what is the acceleration of A if it's initially at rest, if it's moving up the incline, and if it's moving down the incline. All right, so let's set up some force diagrams here. Now, unfortunately, I can't just make one force diagram that's going to work for all these parts. Oh, maybe I can if I get a pencil. And because the frictional force for parts B and C, if the block is initially moving up the incline, then friction's going to oppose that motion. And if it's initially moving down the incline, then friction's going to oppose that. So the friction force is going to be flip-flopping. And then if there's enough static friction to keep it at rest, then I don't know what direction that's going to be, because I don't know if this, like down the ramp force here, is going to be more or less than this. And the static friction would try to balance that if it can be enough. So let me grab a pencil real quick. Be right back. Got one. Doesn't have that much of an eraser, which could be a problem, but all right, we'll do our best here. So this is the block that's on the ramp. There's the gravitational force. Here's my other axis. And I'm going to break that up into its components. There's my 40-degree angle right there. And then, of course, the normal force, keeping things normal here, keeping the block from accelerating up off the ramp or sinking into it, which would not be normal. Okay, and then I don't know what direction the friction force is in, so I'm going to leave that off for now. But I've got my pencil ready for when we figure it out. Then the hanging block is, I think I'm going to leave off, or maybe this is another good spot to do the pencil for this force. I don't really know how much tension there is here, if it's going to accelerate which way. So all I really know is that this force of gravity is equal to 32 newtons. Oh, this pencil might be doing more work than I thought. Ooh, that is a done G2 pen right there. All right, let's see if I can make it into the trash can from here. Made it. Just kidding, I was not. It was kind of close. That was the sound of it hitting a whiteboard that's on the floor behind my desk. All right. So there's the 32 newtons, and then this is 102 newtons. So let's start getting quantitative here, or continue to be quantitative, if you want. So 102 sine 40, that is my down the ramp component. All right. 65.6, and then 102 times the cosine of 40 is 78.1. And so will then be the normal force. All right. So, in part A, we are going to release the blocks from rest. So that means they're initially at rest, which means they could remain at rest if there's enough normal force to keep things real. And then, let's see, I forgot my tension here. That's definitely going to be in this direction. It's definitely going to be equal to this. Okay, so if they're released from rest, at least initially, that means that this would be 32 newtons. So this would be 32 newtons. Now if it starts to accelerate, then it's not going to be that anymore. But what I'm checking here is to see if there could be enough static frictional force to keep this all balanced. Because if there can be, then there will be. That's what static friction does. It balances things if it can. So right now, looking here, I've got 65.6 newtons of force, gravitational force, down the ramp, and I got 32 newtons. So if there was no friction, it would definitely accelerate this way, and then this would not be, that would drop. Actually, it would increase because this would be accelerating upward. But that's not for us right now. So can there be, the question right now is, can I pencil in here a static frictional force that could be enough to balance this? So it would have to be, what would that be, 33.6? That is the question. So let's figure out what is the maximum static friction force. Well, it's the static coefficient times the normal force. And that looks like it's going to be enough, doesn't it? So that maximum static friction that we could get is about 43.7 newtons. And that's going to be enough because I only needed like 33. So that means what is the acceleration going to be? There's enough static friction, so that means the acceleration will be 0 because everything's going to be balanced. All right, cool. Part B, let's see if we can piece this together with like redoing as little as possible. So what if it's moving up the incline initially? So if it's moving up the incline initially, then friction always opposes the direction of motion. So that means my well, it's moving, so it's not going to be static, is it? So that's going to be kinetic friction, and it's moving. So for part B, if it's moving up, now I don't know that that's the winning direction. In fact, it certainly looks like there's not going to be that, even though it starts moving up the incline, it's going to be slowing down because the kinetic friction and this added together are going to be battling against that. So I could be wrong, and if I am wrong, and I do all my work right, I'm just going to get a negative number for the acceleration, which will tell me, oops, hey dummy, you picked the wrong direction. But I'm pretty sure that the direction of the acceleration is going to be this way down the ramp, because I've got this, and that's a whopping 65.6 newtons compared to what's going on over here. So that means that my, let's say this is block 1. I'm going to call this block 1 and block 2. So sum of all forces on block 1 is the mass of block 1 times the acceleration. And for me, I'm assuming this is the winning direction. So that means I've got my kinetic friction and my down the ramp component of gravity. Those are winning minus the tension losing is equal to the mass of that block times the acceleration. And the sum of all forces on block 2, I've got the mass of block 2 times its acceleration. And here, I'm assuming that this is the winning direction, so that means this would be the winning direction here, because they're attached. Ooh, that's hard to do. Move your finger this way, and this one that way at the same time. Oh, that's actually not that hard. You just got to practice. Ooh, that was bad. Like that. And excuse me for 1 second. I'm just going to deal with that. Hello? I'm in the middle of making a video, so I will call him back. All right, thank you. All right, I'll call that person back. All right, where were we? So here, this is the winning direction, so that means tension is going to be winning, and of course I need the tensions to have opposite signs so they cancel out. Minus 32 is equal to M2A. All right, so what is my kinetic friction. My kinetic friction is mu k times the normal force. So that's 0.25 times the 78.1. That's 19.5 plus 65.6 minus t. And then the mass of this, they gave the weight, so I'm going to have to divide that by 9.8 to get back to the mass. And then here, I had everything I needed in place, just got to find that mass. 32 divided by 9.8, 3.3. All right, then I just need to add those equations together, and we should be home free. I think I can just barely fit it on here. So adding these two together, looks like I get 13.7 A, and then 19.5 plus 65.6 minus 32. And divide that by 13.7. And I did indeed get a positive number. So I chose right there. That was pretty obvious, I think. Okay, so let's check that. That is right. They did it in unit vector notation where that's the positive x, so they have negative this I. That's fine. And they rounded, yeah, they made it 3.9 instead of 3.88. Okay, so we're good there. Now, 27C, I really don't feel like redoing all of these diagrams. So if it's initially moving in 27C, moving down the incline, oh, why am I erasing that friction force? I mean the tension force. This is what I need to be erasing. If it's moving down the incline, then the friction force will oppose it in this direction. But I still think that this is going to be winning. So I'm going to gamble on that being the case. That was 32 newtons only when we were in part A, and that was balanced. I don't know what that is now. Okay, so what does that change? It just changes the sign of this. So it's very similar to what I have here. I'm going to pick up from this line right here. So now I have the 65.6 winning, and then both of these losing. Equal to that. And here the friction wasn't at play there, so that equation is exactly the same. So there we go. So what was the, let's see, did I have that? That's 19.5. So now I've got 65.6 minus 19.5 minus 32 is equal to the total mass. Was that 13.7? So that was a little easier because I had a lot of it already set up. It wasn't a lot different. I think the takeaway, does it annoy you when people say the takeaway? That's like a fairly recent development in the English language, people saying the takeaway. The takeaway from this one is that the takeaway right now is I can't talk and use a calculator at the same time. From the problem, it's that the direction of friction, I think that thinking about the direction it's going in each of those cases, A, B, C, was important for us to be able to figure that out. So in the case where we have static friction, what's the direction of static friction? Well, it's whatever direction is necessary to balance things out. because it's static friction. That's what it does. It balances things out. If it's not enough to balance things out, well then you throw that out and you got kinetic friction. And then kinetic friction is easy. What direction are you moving? Kinetic friction is the other way. And if you think that, oh, I'm going to trick friction into helping me, it's like you're going that way, well, I'm going to change direction real quick. Then friction immediately also changes direction. It's a super annoying force in that way. It's not your friend. Just check the answer for that last part. Yeah, that's correct. Number 29, last one. We got, this looks like a fun modified Atwood's machine set up. There's block A, block C, block B, hanging over the edge. That's how the poets talk about physics. And let's see, A and B, 44 newtons for A, 22 newtons for B, respectively. Determine the minimum weight of block C to keep A from sliding if the coefficient of static friction is 0.2. And then we're going to lift block C off. What's the acceleration of block A if mu k is 0.15? All right. So there's a couple ways to do this. One of them is just to kind of think about, like, well, what if this was just all one block here? Because the friction here doesn't know that it's not all one mass, that part of it is this other thing sitting on top. So I could just figure out here, what is the maximum amount of static friction that we have available? And if things are going to be balanced right at the edge of maximum, right before it starts to move, then here for block B, I'm going to have 22 newtons of gravitational force. And so if things are balanced, then so is the tension 22. And then here on this, I'm just going to say block, this AC block, I would have that same amount here, and then that maxed out amount of friction. So what I'm trying to figure out here is if that's 22 and that's 22 and that's 22, then 22 newtons is equal to the static coefficient 0.2, that normal force that's going to keep us there at that condition. So 22 divided by 0.2 is 110. So that's the total amount of normal force that I would need here. Now this block already has 44 newtons of it, so that means the weight of this one would have to provide the rest. So that's going to be 66 newtons. Now what if that was lifted off? That's part A. Well, that means we only have block A now, so that's just 44, and then so is that. And then I don't have static friction anymore, I have kinetic friction. So it's writing my Newton's laws equations here. Sum of all forces on block A, sum of all forces on block B. This is going to be T minus the force of kinetic friction, MA times A. Here, gravity is going to be winning. Add them together, what do you get? So I get 22, the tensions cancel out, minus the force of kinetic friction, which is 0.15, times the normal force. That's going to be equal to the total mass. That's 66 over 9.8 times the acceleration. So let's do some math. Let's push some buttons on the calculator. Let's see what we get. That's what I got. Let's see what the answer is in the book. Oh, it's that. They called it 2.3. All right.